All right, okay, you don't have to click that button here. So, yeah. Okay. All right, well, good morning. We want to welcome you to the fall AIAU forum. Today we have with us Dr. Michael King from Florida Institute of Technology. And today he's going to be talking about face recognition, demographic effects, and the investigative lead. This ought to be really cool. I think you're gonna like it. So at this time, I'm gonna turn it on over to Dr. King. So let's welcome Dr. King.
Yeah, this is it's always great to be here at Auburn, and thank you, Dr. Dozier, for the welcome, and it's also nice to be here in nice weather coming from Florida. Sometimes I go places that is not so warm, but yeah. So I'm gonna give a talk today. I'm gonna talk a little bit about face recognition, but before I start, I'll talk a little bit about myself. And so I spent 14 years in government before leaving government to join academia in 2015. And primarily my research since that time has been focused on advanced biometrics technologies and cyber identity, or identities in the cyber domain, and more recently been working on some projects related to computational psychology, and just trying to be able to understand whether or not you can indirectly assess someone's personality type. So in total over the past number of years, last year my research expenditures were around $2.45 billion, and over the career it's been about a total of $13 million since joining academia. And so, but this is a project that we're going to talk about today that is near and dear to my heart, and it's also one that has some societal implications, and so that is an area of face recognition. There's been a lot of discussion around demographic effects and those types of things associated with face recognition, and more so than that, there's been a lot of concern over events occurring that are in the form of what's determined to be wrongful arrests, and the question is, is face recognition to blame? Does it play a role? We know it plays a role, but is it the fault of the technology that ends up yielding these unfortunate events that are occurring? So we'll talk a little bit about the motivation, and then we'll talk some about the demographic variations in one-to-one matching in terms of the analysis that has been performed. Then we'll talk a little bit about 1 to N, and I'll explain the differences between the two once I get there. And then how it's actually used as an investigative lead, and then some concluding thoughts. So the motivation, you may have seen a report in the 2020 timeframe, in the June 2020 timeframe, about a man who was wrongfully arrested in Michigan by the Detroit Police Department. And so essentially, I'll give you a synopsis. He's at work. He gets a phone call to come turn himself in. And turn himself into who? To the Detroit Police Department. We have a warrant for your arrest. He thinks it's a prank. All right, and he says, if it's a real warrant, then you can, I'm going home in a little bit, and you can meet me at my house or whatever. And I'm just giving you a synopsis. I'm not going to go through the full story. Later on, his wife gives him a call to let him know that hey, somebody's here to see you from the police department. And that's when he kind of realizes, okay, maybe this is not a prank, but still no idea in terms of what he has done that's wrong. Never had any issues with the law enforcement. And so he gets off work. It's a few days before his birthday, probably looking forward to dinner. Drives up in the driveway, and as he drives up in the driveway, he's the driveway is blocked by a police car, as you might expect would happen. He's immediately put in cuffs. He's trying to understand, kind of what's going on. Wife and kids are there observing this whole thing, helpless. And he gets to spend the next 30 hours in lockup. And it wasn't until at some point in time they showed him images of a person who had committed a crime. And they're trying to say, this is you. He's looking at the images. He holds them up to his head and says, "Do you really think we all look alike?" It's an African-American male. And so that's when, things begin to unravel. You begin to ask the questions of like, how did I end up here? Long story short, they took surveillance footage from the crime scene and ran it through a face recognition system, through a large data set, and came up with this guy as a probable match. And so he's forwarded to the police department as an investigative lead. Not necessarily conducting a thorough investigation after that, just one more step, and they in essence go pick him up. And so the actual events around the arrest and around their procedure is a little bit more involved, but I would still call it negligent. And so then you have another young man who, there was a fight at a high school, and one of the teachers or someone was recording. Some kid shows up here in this burgundy sweatshirt and grabs the phone and throws it away. And so they grab the image off the phone and they run it through face recognition, and they come up with this guy, a 25-year-old who probably had no business on the high school campus. He probably wasn't there. So he gets to spend some time in police custody. You would think that would be enough, but then you have Nigeria Parks. And this one was the one that I always said was probably the most concerning to me for a while. There's more. But there was a crime in New Jersey. Again, somebody drops the driver's license, they scan, and then they run it through FR system, and they come up with this hit on Nigeria Parks. And Nigeria is just, adamant that he was not present at the scene. I say this one is the most dangerous because they actually offered him a plea deal. Right, so you plead guilty. We don't have to go to trial. And so, the way this thing works is a friend of mine got offered a plea. You plead guilty, you do 5 years. If you don't plead guilty, we throw the book at you and you're looking at 40, right? If you don't have money to hire an expensive attorney, you take the plea, which is what most people like to see. You take the plea and then there's no trial. And then and then supposedly on good behavior, you're out in like 5 years or so. And so that's kind of the way these work. Fortunately, in this particular case, the judge actually recognized that there was very limited information that actually connect this person to the crime, and so they threw out the actual plea, and so which was a really, really good thing. And then you have I used to think the first one was, I was like, man, that's really dangerous. But then you got this one. It's like this kid is in Georgia. The day after Thanksgiving, he gets pulled over and finds out he has a warrant in Louisiana. And well, they don't immediately tell him that he has a warrant in Louisiana. Later on, they tell him the warrant is from Jefferson Parish, Louisiana. And like, Louisiana, it's like, yeah, because somebody had actually stole something. They saw an image off surveillance cameras, run it through a face recognition system, and this guy pops up as a probable match. So they issue a warrant for his arrest. They arrest him in Georgia, and it turns out he's never been to Louisiana. And so it's and then you had one other young man, and then we'll stop this because, and this is about the end. It's a good thing. It's only 5. And this guy, there was a crime that was committed in Baltimore, and they ran surveillance images again through face recognition, and they came up with a suspect. And the wife views the footage and said, "That's not my husband." And at the time of the crime, we were watching a movie together. And so, but that's still not good enough. He's in jail for a few days before they actually let him out. There was another one, only one more that we know of, that occurred in February of this year in Detroit again. And so this is a lady who's 8 months pregnant, and she's it's in the morning time. She's getting her younger daughter ready to go to school. She's going to carry her daughter to school. She's there with her fiance, and the cops show up at the door, and they have a warrant for her arrest. And so she's 8 months pregnant. She also has a little girl. But there was a carjacking 2 weeks ago, and 2 weeks prior. And so yeah, they ended up taking her down. Now, the good thing about this one is, well, it probably is not very much good out, or helps just positively, but she only spends 11 hours in lockup. And I say only. Now, it's a huge disruption to most people's day, right? And she's 8 months pregnant. And then they realized, okay, there's nothing in the any of the witness interviews that says anything about there being a pregnant person involved. And it's pretty obvious at 8 months that a person probably not likely to be involved in a carjacking, and nobody not noticed that, oh, the person who carjacked me clearly was pregnant, right? So it's a so that's kind of the what's going on there, and so, I used to say that face recognition is a very powerful technology, and but there were some unforeseen consequences of the technology being used by law enforcement. That's not entirely true, and so there's a group out of Georgetown that was trying to sound the alarm for a number of years prior to any of these arrests being conducted, and so they called it the perpetual lineup. And so a crime occurs. There's footage at a crime scene, and then the police department, whoever, runs that image from the crime scene that they were able to take through some repository. This is typically a repository of mugshots, those who have been arrested before, or driver's licenses in cases. And so in the case of Robert Williams, never been in trouble with the law, but his was an expired driver's license that they supposedly came up with a match on. And we'll discuss the terminology a little bit later as well, in terms of whether whether it really is a match or not. And so, and that's the reason why you've heard all of these bans, these calls to ban the technology from police use. And I've gone on record many times before saying that I would never call for an all-out ban of the technology. And I spent a number of years trying to help to develop the technology, and so I would never actually call for an all-out ban. But with some of these cases, I have to be honest with you that I've come very close. And maybe not for an all-out ban, but certainly a ban by certain groups who can't use the technology responsibly. All right. And this is not a bash to police talk either. They perform an incredible, they have an incredible responsibility as men and women who leave their homes, whether it's early in the morning or late at night. As everybody else is running from trouble, they're running towards it. And so it's our responsibility as technology developers to develop tools that actually help them and not put them in compromising position. That's my argument now, with the way some of these technologies are being developed and being deployed. That I think that as scientists, we can do a better job of ensuring that we also protect innocent citizens, and you'll understand that a little bit later on. But it's not just law enforcement now. I mean, these technologies, is with all of AI. AI has been around for years, right? And all these technologies are kind of rooted in some level of machine learning or artificial intelligence. Been around for years, but now, people, the general public, just has greater access to tools that were developed with AI. And so this is a case of, and this is not a legal case, but this was just a situation where there's a guy who, goes to his local drugstore just to, pick up a few items, and this store has been, having some losses to occur. So they install a face recognition system to try and identify repeat offenders. And so, so they have their own little gallery or repository of people that they're on the lookout for, their own watch list. And so you walk into the store, and then before you know it, a manager is accosting you, telling you need to get out the store right now. It's like, why? Because you've thieved before. It's like, what are you talking about? I've thieved before. It's like, I've never stolen anything. And it was the wrong guy. This becomes pretty troubling because, again, this is an African-American male. And when you do some studies in terms of zero acquaintance, ability for a human to be able to recognize or compare two images of a person or a person to an image with zero acquaintance, meaning I don't know this person and individually. And so now I'm just trying to do this ID on my own. You tend to be better at identifying folks that come from within your own demographic. And most of the store owners and store managers are not likely to be African-American. That's going to run into this situation. And so then you have this 14-year-old young lady, again, parents drop her off at a skating rink in Detroit. And there had been some altercation at this particular facility before. And the face recognition engine pretty much says that, okay, this person who's trying to enter now is one of those people that you've actually banned. Turns out it wasn't her. Right. And this is really dangerous because it's, they're saying the system reported a 97% match. My question is, whose system is that? Right. And so it's like that would actually report, because most systems are not necessarily designed that way. And so that becomes a question. So now it's not all bad. So you have this guy who's in Oklahoma City. He got shot, he goes to the hospital for some care. And then he goes, all right, so now he tells the cops, my name is John when it's really Jerry or something. It's like, so then the cop uses the images from the, and that's not Dr. Doty, but it's uses the images that have come from his body cam and runs that through an FR system in Oklahoma City. They're able to determine the real identity of this person and determine that he actually, had a warrant out for his arrest as well. And so that's the reason why he had provided the wrong name. Same thing here. The case in Florida, a guy was about to be accused of vehicular homicide, and at the because he was at the scene, and there was a witness that had helped to pull him out of the car and had told the police that, this guy was not the driver. But he was the one that they had immediate access to. And so he was going to be charged with vehicular homicide. And so they used a technology that was developed by Clearview AI to search for the person on the body cam. And is anybody in here familiar with Clearview AI? So since you're not familiar, I'll tell you a little bit more about what this company does. And so a lot of people are trying to ban their technology. What they do is they scrape images from the web. So if you have Facebook, Instagram, LinkedIn, your Auburn University website as faculty members, chances are your image, if it's publicly available, your image is in their database. And so they scrape the web for all the images that they can actually find. And then they developed face recognition technologies. And so now they sell that to law enforcement and access to other people as well. And so this was kind of like a goodwill story that they made the technology available to this lawyer. And so, because they needed some needed some good publicity or change. And so they used their technology, and they were able to find out who the person really was that was at the crime scene that night, because they didn't keep that information, didn't keep the contact info. And so they were able to track this witness down. And so that's a good use case of the technology. So what does the technology do? So face recognition technology, there was another slide that I was looking for just before the presentation, but to give you a little bit of background, most of the face recognition systems today are developed with deep convolutional neural networks. And so these networks basically extract unique features from images of people. And you compare these features, and if they project to the same space, in this hyperdimensional space, then you should produce a high similarity score. And that's what we're looking at in here. When we do a lot of this analysis, we tend to look at score distributions. And so you take this large data set, and the data set that we use now has about 200,000 images in it. All right. There are others that have about 12 million or so that are generated by NIST. And you do all these cross comparisons. And so I want to take every image in the data set that I have of myself, and I want to compute a score for each one of those comparisons, each one of those unique comparisons. And my desire is for those scores to be really, really high, right? And those are what's called mated comparisons. And so it's two images being compared of the same person, and then you do this for hundreds of thousands of people, or millions and millions of images, and you end up with this range of scores that are produced when you're actually computing, the scores for two people when the images are of the same person, right? And what you really want is for every image of myself to produce a score like a 90, 99, 100, right? But that's not always the case. Sometimes these things can get really low, and this is particularly true when the quality of the image itself is substantially reduced. And the other type of comparison is the non-mated comparison. And so the non-mated comparison is when I compare an image of myself with Dr. Seals. And so when you're doing that, you want these things to be as low as possible, right? And ideally, there'd be zero, but that's not the case, right? And so you end up with this range of scores. And so, the most populated scores would be in this mid-range. But then you have a few stragglers that form like this intersection. And so when you're going to build a system, your question is, where do I place the decision threshold to say whether or not this person is legitimately a mated comparison, or such that the score is above the threshold, it's a mated comparison. And if it's below, it's a non-mated, right? And so, or these two people are not the same. So the mated side, they're the same. Non-mated side, they're not the same, right? And that's really becomes the question of, where do I actually draw this thing? And so as you're trying to figure out where to place this threshold, it's inevitable that there's going to be scores that should be on the right side saying that this is the same person when you're dealing with low quality images that are going to fall below that line, right? And it's going to generate what's called a false match, or false non-match, where what should have matched did not. And then you have the other side where, if you move this decision threshold too low, then what actually happens is there are going to be some comparisons of two people who are not the same that are actually going to cross over this threshold to the right side and the system will say, oh, these two are the same. And that would be what's called a false match, right? And so what we try and do with all these situations is minimize the number of false matches. Okay, and that's based on this whole threshold placement. And one of the ways we look at the overall separation of these two distributions is based on this D prime statistic. We've been using the D prime statistic for a while now, and we're moving on to other measures. But and we kind of understand in order to use this, this is intended for the cases where you have a normal distribution or Gaussian distribution. We get it, but but one of the things that we want to do is just to take a look at this separation between these two distributions. Ideally, you want a valley. If you have a valley, then you're good, right? And eventually, maybe we'll get there, but we're not there yet. And so when we started our studies, we were looking at one of these older technologies that's called ResNet in the deep convolutional neural systems. And we started looking at this because there were some suggestions or statements that, face recognition technology didn't work as well for people with darker skin hues or primarily Black people. And so we wanted to do a study just to see. Now, I have to always caveat a lot of this. I took out a lot of slides that explains the composition of the data set, but it's primarily African American and Caucasian. It's a mugshot data set that was actually scraped from the web. And so a lot of times when I'm giving these presentations, everybody who is not either African American or Caucasian wants to know, like, well, how well does the system perform on us? And so but large numbers of other demographics just aren't represented well in a lot of these data sets. And so we don't have the data to do the analysis. And so therefore we do it on the basis of the data that we do have. Right? And so with that, we look to see, and so you look at these distributions, and the Caucasian distribution is in the blue, and the African American distribution is in the red. And you see the dotted line represents the mated scores, and the solid line represents the non-mated scores, right? And what you can see is that for each one of these, for the African American mated distribution and non-mated distribution, both of the sets of scores kind of shift towards higher means. So on average, those scores are a bit higher. And that's what would generate a higher false match rate for the African American population, because if you were to draw this decision threshold here at 40 or even here at 50, you'd have a higher number of African Americans that are scoring on the other side of the decision threshold than you would Caucasians, right? And so that would actually generate a greater number of false matches. And sometimes these false matches are on the order of magnitudes greater for one demographic group relative to another. And you see the same thing for for another COTS system that we actually use as well. And so, but when you take a look at it, the separation of the distributions is about the same for both demographic groups. So what it says is that the algorithm's ability to discriminate between the two different demographics is roughly the same. The challenge comes when you have to do it at the same time, right? And so, because now I have to develop a system that works for everybody equally well. And so that's where a lot of this challenge actually comes in. And so you can set up these thresholds, but it's impractical to say that I'm going to have a data set where I only need to worry about African Americans, or another one where I only have to worry about Caucasians. And so that's the issue that we're trying to get beyond. And then when we break it down a little bit further, we began to look at, like this in terms of gender as well. And so you have Caucasian male, you have Caucasian female, African American male, and African American female. And what you see is this black line here is has the farthest shift over to the right. And so that represents a higher probability of generating a false match for that particular demographic group. And so that would be the African American female, followed by the Caucasian female, then the African American male, and then the Caucasian male again would experience the lowest probability there. And so what's really interesting is that you have this shift for the African-American population relative to the Caucasian population. And then when you break it out by gender, you have yet another shift where the women actually go even further over to the right relative to their male counterparts. And so when you now look at the mated scores, then you tend to look at the Caucasian female has the greatest probability of generating a false non-match in this particular case, followed by the Caucasian male and the African-American female and then the African-American male, which means that from a mated score probability, you're more likely to get it right when it is an African-American male, right? And that's pretty much what this says. And so when you're looking at two images of the same person, if it's an African-American male, they tend to produce a higher score and it tends to be the correct one. All right. So many people would say, well, you were doing one-to-one in this scenario that we look at in terms of law enforcement use. It's not a one-to-one comparison across everybody in the data set. It's really a one-to-many. So I take just one image of myself and then I project it into that database to see, you know, who has the greatest similarity to my face, right? And that is a one-to-many type analysis there. And so therefore, you know, when we're doing this analysis on the mated side, we don't look at every, like if I had 10 images in the data set, I wouldn't look at all 10 because the probability that I might end up with a high scoring one all the time would be really, really high. And so what you want is you want to understand this range that you end up with. And so in this particular analysis, we took a look at the best scoring mated comparison against the best scoring non-mated comparison, right? And so it's like I want to understand, you know, the scores when the best score that's generated with another image of myself, and then I want to understand the overall distance from the best score that's of an imposter, not from the entire distribution, but just from who is that person that this computer is saying looks most like me, right? And I'll show you a couple examples that my students did for me, you know, before too long here. So you have a probe image here. This is an example of rank 1 errors, and so this person goes in the data set. These two labels says that these two images are the same person. This person, I swear they look a lot alike. But the labels are pretty much saying that no, that is not the person. That is not the same person as the probe image, right? And so these two images would be in the gallery. This would be my probe image. I go into the gallery and I'm looking for this for the person who looks closest to this one, and then it's like yeah. And so then this is an example of an error that the system says that we encountered. Here's another one where this young lady, we use this image as a probe. We projected into the data set, and her highest scoring mated image was actually a rank 4. And then there's this is an example of another person that scored higher than her own image. This one I think was interesting in itself. I don't know how this came up with a 0.99, because this one, in my opinion, looks, you know, much closer to this rank 2 comparison here that says the probe. Well, what do you see as a challenge in this image? Just looking at the quality here. Light. So lighting actually has a dramatic effect on the ability of these systems to actually produce high scores. And so for lighter skin tone people, you know, taking an image that is overexposed, which causes your sensors, the pixel to reach full well. Essentially, there's no information there. So you reach this clipping point and your sensors become saturated. And so there's really no information in these areas. And so so from a sensor perspective, it's called full well capacity. And so that's likely what drove this score down. On the African American side, it's the underexposure that causes you issues, or on the darker skin tones, because you can't get contrast there either because everybody's so dark. And so there's no wonder why this person ranked at 456, really, because his head wasn't even present, right? And so this gives you an example of, for a lot of these systems, the quality of the images that are used could be very, very poor. In the interest of time, let's get the only thing that I'll say about this is that if you're a Caucasian male, you tend to produce other scores closest to you when being compared to other Caucasian males, right? And so you generally produce scores that are closest to you on the non-mated side, based on those that come from within your own demographic group, right? And so cross demographic, false positive identifications are rare, and so that's these things are rare in the first place, but really across demographics, they're really rare. We began to take a look at the criminal investigations that we went over before. A crime occurs, and this came from Rank One's website, a blog that was a blog post there. So a violent crime occurs, an image of a perpetrator or a victim is available. You pull it from the frame from the surveillance camera. An investigator analyst searches the image across the database. In the case of Williams, it was 49 million. The candidate list is returned. And the other thing about searches against the database, when a system is used as an investigative lead, a lot of these systems by police departments, the quality gate, you would accept lower and lower quality imagery because you already know it's coming from surveillance cameras. And so you're not going to have this pristine driver's license photo that you're going to compare against. Threshold. I told you needed a decision threshold, right, in order to generate a match. And so we'll talk a little bit more about that one later. Ask me about the threshold. And then the candidate size. So this looks into a database of millions, hundreds of thousands or whatever, and then pulls back for the person some number of those images that generate the highest scores. It could be 50, could be 10, could be 200, could be 500, right? And now the human has to, go in and take a look and see which of these people are actually a match. And so if they think they have a match, they generate what's called an investigative lead report. And so that's what happened in this particular case. And so as we look at this lead report here, for your other neural net types, the other thing that I would say to you is that this is the probe image, and this was the image that was returned back from the gallery here on the right side. All right, this probe image is lower quality, right? And it's taken from a full 1920 by 1080 p surveillance frame, right? And so, but then when they crop out the person's torso, you have fewer pixels to work with. When you're doing face recognition, the only thing you're really cropping everything beneath this hat bib, getting rid of everything else in the background to the left side and to the right side, and then you're estimating where this person's chin stops. That's the head. And when you do that, the resolution drops all the way down to like 43 by 44. All right. The input resolution to an image resolution to a lot of the open source algorithms around 112 by 112. So therefore you have to interpolate the image. And when you interpolate the image of a person's face, right, you're adding information that was never there. Right. And so it's not one of these things where you're projecting, increasing the resolution of like the size of a window, right? Where it's a straight line, there are blinds, this, that, and the other, right? And so now you have a whole lot of stochastic stuff that is occurring on the face. and you're trying to project that onto these you're trying to interpolate up so you can feed this thing into the neural networks. The other thing is to pad was a whole bunch of zeros, but I don't know who would do that. But anyway, so as the resolution decreases, so we did some experiments, and as the resolution decreases, so too does the mated score distribution get closer and closer to the non-mated scores distribution. And for that reason, a lot of people would actually forego the use of a threshold when using a face recognition system for as an investigative lead, right? To generate a lead, because your scores are not going to be high. Even your mated scores are going to get low. And as they get low, the biggest thing is I don't want to miss the person that I was looking for. So the system doesn't generate matches. It generates comparisons with the highest similarities. Right? They're not matches. And so when people say that face recognition got it wrong, the system didn't get it wrong. It was designed from the onset, not to institute a correct answer. All right. And so let me show you. So I had my students, they're great characters, love them. So we were in class last semester, and we have this database, like I said, of 200,000. I said, to really drive this point home, let's take this database of 200,000, and I'm not in the database. So why don't you take 2 pictures that you can find of me somewhere, and run them, do some comparisons across the people in this data set, and show me what you come back with, and just show me the top 10. All right. These are the 2 images that they decided to use. There's one here, and this one is a much slimmer Mike King, but it was, his face is thin and everything, right? But this is me of a few years ago. And that image was, each one of these images were used as a probe image. So they used the first one, and this is the list of candidates that came back. Normally for this matcher, you would need to score above a 0.7 in order for to say that these 2 reasonably could be a match, right? In this particular case, but this is what a human analyst for a police department would actually get back if they only wanted 10. I will tell you in the Roberts Williams case, they got back upwards of pretty close to 500, 486. And now the human has to go through and try and figure out which of this 486 might be the person I'm looking for. And the other thing about Robert Williams in Detroit is he was in position number 9. That is rare for a lot of the systems I use today. But I've never had access to 49 million images to be able to prove it. All right. And so I don't know where you might find your person in that size of a database. But yeah, that's high scoring. The other thing that you notice is that a lot of these people have beards. Right? Same person, I'm the same person. All right. And here, I get some feminine characteristics or something going on. I don't know what's the top score here is actually increased. Right? And so now a human looks at this and they could pretty obviously say, okay, none of these actually come close to, and maybe I'm overly confident because I know what I'm supposed to look like, right? But if a person who's never encountered me before might not have that level of insight, and so that's kind of what they end up dealing with from an investigative lead perspective, right? And so the only thing that the new stuff that I'm pretty much saying now, and I'm going to drive home in a paper here pretty shortly, is that the demographic differentials in terms of accuracy from one demographic group to another, it does exist. All right, but for a lot of the while these differences are present, I think they're manageable in a wide range of applications, especially those applications that involve the federal government and in several municipalities. Now, not so much for instances where we talked about the drugstore and the skating rink. Right, there's some issues there that we need to deal with. For the investigative lead use case, the error rate should be nearly the same for each demographic. All right, what that means is that if you use the system to generate a list of 200 candidates, right? If the person is in the database, the person that you're searching for should be in that list of 200. The other 199 are going to be errors. And that should be the same regardless of the demographic that you're looking for. Okay. If the person that you're looking for is not in the database, the system is going to be 100% wrong 100% of the time. All right. You know, the United States is a relatively, it's a very diverse population. And so the one thing that should concern us all is that every single one of the 6 wrongful arrests and wrongful detentions were all Black people. 5 Black men and 1 Black female. So it's like, that's the one thing. I mean, there's nothing scientific when you look at the technology that says that should be the case. All right. And so I do believe that we should implement a quality gate. There's some instances where probe images, especially when you get down to, I told you the resolution was 43 by 44, and the interocular distance, which the number of pixels between the eyes was roughly around 17 to 20. Typically, you don't want to do things that are less than about 35 or so. You want at least that number if you're going to do this type of thing. And so a quality gate that kind of cuts this mess out is one. The other one is implementation of a threshold. When you implement a threshold, though, the one thing that will then begin to manifest itself will be the differences in terms of the false match rate from one demographic to another. So there is no free lunch, right? But I think I'll take my chances with the quality gate and with the threshold, because it at least says that now for someone to come in and detain you, that the score had to at least be above a certain amount. The other thing about these scores is analysts are pretty much trained to ignore the scores and not look at them at all. But now the technology, I believe, has advanced to the point where I trust the score over the human. And so just generate 1, no need for a person to have 500. Just generate 1, 2, 3, or 4, especially for local law enforcement. And federal government, they have the resources to be able to adequately vet these things. And they have a high degree of accountability of a number of people asking questions. Local law enforcement, maybe not. Right? And so again, the job is challenging, but these are things as we worked on the development of these technologies that I just did not anticipate these types of issues. And we don't want these types of things to continue to occur moving forward. And so with that, I'll stop. And if there are time for questions, I'll entertain questions and we can go from there.
Okay, are there any questions?
So on slide 13,
yeah,
we were talking about we'd like to see decision boundaries actually implemented in these. So looking at that chart on the left, it looks like it would be difficult to select one that would work for everything. Is there any case where you would want to have multiple decision boundaries? Because I could see 2 points you could draw on there that would minimize mistakes.
Yeah. So let me just say that there have been went too far. It showed you really good stuff. But anyway, so some scientists and I should say that a lot of this work was done with a close collaborator of mine at the University of Notre Dame. He was of the mindset at one point in time that you know, we should first test for the demographic and then determine what the threshold should be. I think when you use this for law enforcement, if you ever go into a courtroom and are you ever being deposed as an expert witness or whatever, and you tell people that you use different thresholds for Black people than you do for white people, I just think that is that does not make for a beautiful discussion with an opposing attorney, right? The other thing is that it's intractable, and so we put some language that was close to that, and in one of our papers, and NIST, you know, pretty much took that language, and a good friend of mine, Patrick Grover, we know each other in this scientific circle very well, and you know, he took the opportunity to write the very last page. You know, anybody reading it reads the executive summary and the conclusion. The very last page of the conclusion, he spent that page dealing with that, you know, that notion of using different thresholds for different people, right? Thing is that I just talked to Patrick, you know, months prior to his report coming out, about a year prior to his report coming out, saying that it's intractable and we could never do it. He essentially put that in the report. But he pulled the text from the paper, and he put it in his report that yeah, it's intractable. You know, this is all the reasons why it don't work. The first thing I gotta do is determine the demographic, right? And so one of my closest friends, his mother is African American, very dark skinned, and his father is white. What's the threshold do I assign to him, the Black one or the white one, right? And in order to determine that, you'd have to extract some information from his image, all right? And now, if it's ever going to be done, the way you do it is it has to be naturally imbued in the algorithm itself. That's doing the cost projections, right? And it need not be known or explained to me that the algorithm is making this type of compensation on the basis of what it sees in the image, right? And so I do believe that those types of adjustments can occur, not necessarily different thresholds, but different, you know, cost functions are being utilized, or different parameter sets being utilized on the basis of what I'm able to extract from the image itself. I think we'll actually get there, but I don't think, you know, I'd ever want to go in a courtroom and say, yeah, I chose this threshold for him for this reason, and so I think that's just a recipe for disaster. I have a newfound respect for the law in that process now. Any other questions? You can go ahead.
I was wondering about the lighting. Is there something that you can do to a picture to pre-process it and maybe lighten or remove some of the dark areas that might improve processing?
Yeah, so it's fairly common that all of these FR engines will do some type of image processing up front. What's actually done, you know, you'll never know from a commercial perspective, right? But you know, you can look at some forms of history. I mean, all of us would have taken the same image processing classes, right? Or pattern rec classes, and you do some form of histogram equalization in terms of the pixel density and stretching out the pixel values in the range where you want to try and generate some additional insights or contrast. And so yeah, so there are a number of those techniques that would actually use, but you know, the reliability of those processes and what's actually being done under the hood from a commercial engine, you just wouldn't know. And so we have tried to play around with some of those pre-processing techniques to improve these things in the past. And what I will say is that you can generate improvements on the mated side. The non-mated side appears to be pretty stable from a quality perspective. Now, as you introduce more people and introduce more images of people, that increases the likelihood that there's going to be somebody with facial characteristics similar to yours that's introduced to the data set. So therefore, that population may actually cause the population increase may actually cause a shift. But in terms of the image quality, it pretty much the imposter distribution or the non-mated distribution tends to stay about the same.
And one other quick question related to your classroom exercise, where they were trying to find a match on your picture. What if you, I guess, injected maybe one close match into the system to see how well they were able to identify that?
Yeah, so the so NIST, Patrick Ruther did this experiment with the 12 million. And most times, when you do that, it will generate the closest matching image at rank 1. It will produce your image in a database, a large database, even a 12 million, high quality, will generate a score that's the top score, right? And one of the conversations I was having with Grother recently was that when we talk about the technology, we tend to talk about the technology using an experiment that you described, pretty much. And it being able to do this 99.99% of the time, your image will show up at rank 1, right? The thing is that configuration that gives you 99.99% accuracy at rank 1 will produce 100% wrong at rank 1 when you're not in the database, right? And so that's the other part of the equation that we have to make sure that we communicate about the technology. Because when people hear 99.99% accurate, that's all they go and that's all they go and say, oh, this technology is 99% accurate, right? They never follow up with the other statement of, oh, but it's also 100% wrong if you're not in the database, right? And so, and that's the other part of the sentence that we got to make sure that we begin to include. Yeah. You have one more, yes, quickly.
Go ahead, and then we have one.
So how can you identify the person if he's wearing a mask or wearing a glass?
So glasses are problematic because the most discriminative information for face is in the ocular region or in just around the eyes. And that's one of the reasons why you wear thicker rim glasses. Right? And so for face recognition, none of these skinny things like just glass, all right? Because I need these rims to kind of distract from. And the other thing is when I go in airports, it's a ball cap, ball cap pull down and these thick rim glasses and keep it moving, right? And so it's like those things actually will introduce errors in the system or cause the scores to be lower from a comparative perspective. And so the thing is, if the features of the face are not present, the features of the face are not present. So there have been some tests done during COVID time of people wearing the mask over the nose. And so primarily what was being used at that time was the ocular region of the face in order to be able to do really well in terms of face recognition accuracy. But there's a lot that goes into the quality of an image, right? We talked about lighting. We talked about facial expressions. We talked about decorations in terms of hair. We talked about accessories in terms of glasses. We talked, a little bit about orientation and perspective in terms of, am I looking directly at the camera? All those things create these confounding factors. They interact together. And they could all actually do things to actually decrease the overall accuracy of the system. So it's not just one thing. It's a number of things that you have to be able to deal with when you're looking at the surveillance characteristics. Yeah.
You have a question out on Zoom. It says, you mentioned the dimensions and pixels of the image plays a role in accurate recognition. Is there a way to set a threshold for minimum resolution or size?
Yeah. And it's just very simple. You look at the raw image, and if when you extract the face, put the bounding box around the face, if it's not above a certain threshold, whatever threshold you set, then you just don't process the image. I would advocate for that. And the other reason why I would advocate for that, most of the studies that are done with humans record. So these processes with the investigative lead also have a human in the loop. So the candidates are produced to the human now does some type of morphological analysis and then makes a determine like, all right, this person has facial characteristics similar to this other person. And then it's like, and whichever one seems to have the most or crosses whatever this imaginary threshold is, it's highly subjective, right? You're the one get put on this investigative lead report to go forward if the human examiner chooses to do so. The other dimension of resolution is when a twin study that was conducted by Dr. Jane, and I'll go and talk to him on Monday. But they looked at the resolution that you needed at least 75 pixels for a human to be able to identify, uniquely identifying. When I say 75, that's the interocular distance, right? The number of pixels between the eyes, right? And that was always full frontal, right? For a human to be able to say, yes, I can spot moles at this point, wrinkles, and this type of thing here, and also here. In these surveillance in very low resolution, as I give this low resolution probe image to a human to do that morphological analysis, there is nothing at that resolution that a person can actually find that they can say is unique to this individual, right? Nothing, right? And I'm already on the record as saying there's nothing there. So it's like at that resolution and the resolution of the first case that I showed you, right? You can't come away with that and say that I was able to identify moles or scars or these type of wrinkles or get these measurements from this area of the face, and it matches exactly what I'm able to see over here, right? What comes back is more generality. Hairline or beard, which could change, right? It's like skin tone, and look, I normally always say this before I give these types of talks, and that is that, if I say anything to offend anybody, charge it to the head, not to the heart. But also to have a part of an honest conversation. What it really sounds like, what the African American community has already experienced before, and we already recognize the language. The language is like, you fit the description, and it doesn't take very much, right? You're black, male, light color shirt, fit the description of who I'm looking for. And so let's have a conversation, right? And so again, I don't want to minimize to any degree the challenge that law enforcement has to deal with on a daily, and most of these guys do it remarkably well. And it's these few times that we tend to highlight, but most of these ladies and gentlemen in uniform, they do their work remarkably well, and it's not a job I'd want to do. And so that's, but in the community, that's just, if you're going to have an honest conversation, I think we get farther that way. But yeah, all right. So I may have said too much there. I'll stop.
Thank you so much.
All right, we good?
No, thank you. Oh, and you still have some coffee and donuts in the back if you all want some.
Or say thank you for the talk.
Good.
Good one. And then previous ones that are like this at the end, they've kind of reached a conclusion that maybe the algorithms